Hello, good afternoon. Welcome to the Perspectives in AI seminar. This is a seminar hosted by the Center for Artificial Intelligence. The center is a partnership of IBM, University of São Paulo, and FAPESP. And almost every month we host some of the most important researchers in artificial intelligence and related areas in this seminar. This year, this month, we have Professor Trevor Darrell of University of California, Berkeley, as our invited speaker. Professor Darrell is on the faculty of both the computer science and electrical engineering divisions of the EECS department at UC Berkeley. He's the founder, and he co-leads the Berkeley's Artificial Intelligence Research Lab. It's called BAIR. The Berkeley Deep Drive Industrial Consortium, and recently he launched the Bear Commons program in partnership with Facebook, Google, Microsoft, and other companies. He's also the faculty director of the PATH Research Center at Berkeley, and before he was leading the Vision Group at the UC affiliate International Computer Science Institute in Berkeley. I know Professor Darrell from my time at MIT. We were colleagues there. When he was doing his PhD from 92 to 96 with Professor Sam Pentland. After that, he joined Interval Research for 4 years, and then went for MIT in the Electrical Engineering Computer Science department, and later joined Berkeley. So I would like to say that if for people who want to ask questions, please use the YouTube I will be collecting those questions and later ask Trevor. And without much ado, I invite Trevor to stage. Thank you.
Hi, thank you very much for that introduction. It's great to see you again, Claudio, and it's great to be here. I wish I could be there in person. It would be exciting to get to visit, but we'll have to save that for a future time. And I'm happy to be here today and to speak about work at Berkeley that we call fully unsupervised and advisable learning, and I'll explain that as I go. I also will feel free to jump in with questions, especially Claudio, if you feel there's something that would be useful for me to explain to the audience. It's hard when it's a virtual talk to understand where the room is. And today I'm going to be speaking about unsupervised learning and self-supervised learning. I'm going to actually assume this is a fairly somewhat understood term, and I'll look to Claudio to see if he nods yes or no, or whether I need to explain more. We've in AI research, supervised learning has brought us great success, especially in computer vision. But there's great excitement now in how can we move beyond this requirement, sort of the shackles of supervision, to learn representations from the data itself, or from tasks that are naturally present in the environment. And I've sort of thrown a few references here to Alyosha Efros at Berkeley, Jan LeCun, of course, at Facebook, and Andrew Ng expressing these ideas early on, that we really can't rely on labels and on supervision. And so that's clearly a dominant paradigm, and there are hundreds of papers coming out now on how can we learn representations not from human curated labels like ImageNet, but instead how can we learn from the data itself, from natural tasks that are inherent in the data, of course also potentially from clustering and related techniques. So many different, and I'll focus primarily on computer vision for this this talk. A classic and effective paradigm for self-supervised representation learning is context prediction. Can you predict one part of an image from another part of the image? In general, that idea goes back, decades ago, at least to the work of Ando and Zhang in 2005, where you predict one part of a signal from another part of the signal. Colorization, can you take a signal, remove the color, and then predict the color from grayscale? Dominant rotation prediction, can you, given an image, predict what's the dominant orientation of the image? These are all tasks that are naturally available in the data that we call self-supervised representation learning. And what's quite exciting is that these tasks have, especially in recent years and even months, shown that we can do representation learning that's as good as, or sometimes even excels, supervised models. But let's be careful. I argue in this talk that there's a considerable amount of, I don't really want to say cheating, but sort of extra information that's coming in around the edge. And I've characterized this as actually augmentation engineering, because a lot of the paradigms that we find in the self-supervision paradigms that we find implicitly take knowledge of what is the downstream task and define self-supervised tasks or augmentations or augmentations in contrastive learning that are known to be acceptable for the downstream task. But in general, we don't know that. We have we should presume no knowledge of an unlabeled task. So that's the theme of today's talk. How can we have truly unsupervised learning? And as evidence of this, the risk of augmentation engineering, I'll refer you to one of the most prominent augmentation and one of the most prominent self-supervised learning papers that are out there, the classic SimClear paper. And you can look in the paper itself. It basically goes in and finds the data augmentations and hyperparameters that are most effective for the downstream task using supervised feedback. So they explicitly say which transformations help and which transformations don't help in terms of learning the representation. And it begs the question, what do you do when your unlabeled data don't have any labels, right? I mean, we really can't assume that we have any labels at all for calling it unlabeled data. And so that's the sort of slightly tongue-in-cheek characterization of fully unsupervised learning that I'd like to put forward today. And we have three papers, or at least 2 papers on unsupervised learning and 1 on adaptation. And the first is one that we published recently called "What Should Not Be Contrastive in Contrastive Learning." And we think of this as a multitask self-supervision approach, where we explicitly adopt a leave one out paradigm so that whichever augmentations or whichever transformations turn out to be useful are available for a downstream task. But if some transformation turns out to not be an invariant property in the downstream task, it's still available in the representation so that you can learn it. You don't have to throw out color, for example, if color ends up being important. A second is a very simple idea that we've explored called self-augment, which is using a metatask itself to predict which other metatasks to bring to bear on a problem. We call this self-augment. And then last but not least, we have a paradigm for fully test time adaptation, which certainly doesn't require any target domain labels. But here we're moving forward even further in a domain adaptation setting and removing the restriction for a source, even access to the source data at test time. So we call this fully test time domain adaptation. So I'll go through those those three things. And just to reiterate the underlying premise of this talk, we want methods that are fully unsupervised, in that we have no target or downstream labels, or even implicit knowledge of what's appropriate in a target or downstream domain. And we have no source data, either images or labels, at test time when we're doing adaptation. So first, what should not be contrastive in contrastive learning? And contrastive learning is very, very popular. Tremendous increase in papers in the last 2 years. It's a generalization of metric learning, representation learning in many ways, unsupervised, of course, but with the paradigm that you take a positive instance and you add augmentations of that positive instance. So you might take an image, take a random crop of that image, and then set up a learning paradigm where you learn an embedding function such that both of those project to the same space. And then you take random pairs of negatives and enforce that they project to different places. So here you have examples of the positive and the negative. So this would be colorization as a possible augmentation. Now this is great, except when it's not. And I think it's self-evident that different tasks will have different kinds of invariances. Some tasks will be invariant to rotation. Other tasks won't be. Some tasks will, for example, coarse-grained classification. Well, you benefit from color augmentations and you benefit from texture augmentations, but you might not benefit from rotation. Fine-grained recognition, it turns out you don't really benefit from color augmentation or rotation augmentation or texture augmentation, because the specific differences in fine-grained are so particular. And as a last example, if you actually focused on fine-grained recognition of flowers, well, actually rotation invariance does turn out to be helpful. So how do you know ahead of time, if you're following in this paradigm of contrastive self-supervised learning, which augmentations to use in your representation learning? And I hate to say the emperor has no clothes, but this emperor is wearing some pretty skimpy bathing suits, because they assume downstream knowledge when they pick the augmentations that they report in their paper, from which they get all of their great results. So at best, you should call this few-shot learning, because they have labeled data that they use for hyperparameter tuning, which is totally fair as long as you represent. And it's very exciting and very important work. I just wouldn't call it fully unsupervised learning. So we've developed a contrastive learning paradigm, multitask contrastive learning paradigm, that I would call fully unsupervised. We call it leave one out contrastive learning, Luke. And the general idea is to allow a family of possible augmentations, colorization, rotations, croppings, and so on and so forth, and to build a set of embeddings that express all of your augmentations except for one. So there'll be some embedding space in which color still matters, or some embedding space in which rotation still matters. And indeed, if all of these things happen to be good together, there's an embedding space, the general embedding space V here, where all of the augmentations are learned together. So if you have the most coarse-grained recognition problem, it'll still have success. But we learn these other losses as dependent spaces, and either concatenate them together or learn them as multitask heads on top of the underlying embedding space that we use for representation learning. So we show the example here for 2, but it could be extended to an arbitrary number of augmentations. So you can see that for different tasks, the each of these augmentation-dependent heads turns out to be more or less useful. So for ImageNet categories, texture and rotation turn out to be important. But for iNaturalist, they all turn out to be somewhat important. And we see strong recognition performance on a variety of fine-grained recognition tasks. Importantly, our models do no harm for classes, for recognition challenges where actually all of the augmentations are useful. We do as well as the existing methods. But for recognition challenges where one of the transformations that would have been added to the standard contrastive learning paradigm actually does some harm, for example, color augmentations for fine-grained recognition, our method maintains sort of closer to optimal performance in contrast to the baselines. And here we see results for our method on a large-scale experiment tested on Naturalist 1K. And we can see significant improvements for our Luke method over the MoCo method. So that's the first result I really wanted to get across. It's supporting the general notion that these contrastive learning methods with a self-supervised paradigm of augmentation-based contrastive learning are effective and useful, but you should not. You should fully disclose the use of some amount of labels in the downstream task or the target domain to do the hyperparameter setting of which augmentations to use. And if you don't, and you shouldn't necessarily call that unsupervised learning, and consider this method that we've just offered, which actually allows multitask representation learning with multiple heads, each head corresponding to the absence of one augmentation. And that turns out to be really the best of both worlds, and indeed we call a fully unsupervised method. Next, I'd like to discuss a complementary idea that we call self-augment, self-supervised data augmentation policies for instance contrastive learning. It's similar to the Luke method, but here we're going to, instead of, whereas the current methods require labels for downstream, for augmentation selection, we're going to see if we can kind of double down on self-supervision and find a self-supervised task that tends to be quite predictive of which other augmentations to use, and explore that direction. And so it turns out that rotation prediction itself is highly correlated with other augmentations. So let's take a practical example and consider the prediction performance linear class accuracy as a function of different possible measures. One being info NCE, another being the contrastive top one accuracy, and the third one simply being the linear rotation accuracy. And here we're showing the performance across a whole set of possible augmentations. Each color here is a different augmentation. And the top one, the contrastive top one accuracy and the info NCE score don't tend to be terribly correlated with the actual linear class accuracy of a model that would incorporate that augmentation. But it turns out that the linear rotation accuracy is fairly correlated with the predicting the performance of linear class accuracy, as we can see on the right-hand plot here. Contrast augmentation happens to be one of the most significant in terms of improving the linear class accuracy in this example, and also has the highest performance in terms of linear rotation accuracy. And this correlation turns out to be true across a surprisingly large number of data sets, including the ones shown here, both for linear class accuracy for the top 3 examples and for AP for the bottom 3 examples. So our proposal in this work is to actually use rotation prediction to set these hyperparameters of what other modalities to use, and in fact perhaps even set other parameters such as the size of a crop, for example. So that's so we've checked the first box here, establishing that a signal is correlated with downstream performance. And let's now go and see how the performance compares to actually using labels from the downstream task. So we determine the base augmentation by training MoCo on a single transformation for 10% of the training period, and then we select the single transformation with the highest rotation prediction. With this base augmentation, we train MoCo and then evaluate the augmentation using the self-supervised lost on the held-out data. So here we can see the results of this method. Self-aug achieves comparable results with 2 unsupervised evaluations and performs better on a number of different data sets even than supervised feedback. Here we're characterizing MoCo as being supervised feedback because it's using supervision to select which augmentations to use. So the conclusion here is that self-supervised prediction provides a compelling way to evaluate learned representations without using labels. And we are thinking of this as part of a large family of end-to-end unsupervised representation learning, which might explore a number of different architectures, augmentations, and ultimately hyperparameters. And this work really explored how we can set the possible augmentations and maybe some of the hyperparameters of unsupervised learning. And there are some additional results and more recent results than were in these slides in the final paper that's available on arXiv. So I'm going to push forward and talk now about adaptation and what we call fully test time adaptation. Again, how does a model evolve when faced with a new environment, and to do so without labels in that environment? And the key idea is to minimize the uncertainty during inference of a representation. And we show that that improves generalizations to corruptions and domain shifts. So I'm going to show a number of examples from from a typical setting in autonomous driving, computer vision for autonomous driving, where you have an image of a city scene, and you would like to label the different classes of driving affordances, what kinds of objects are in the environment, whether it's a motorcycle, a person, a vehicle, so on and so forth. And this is useful for autonomous driving, obviously. It's called, often called semantic segmentation. But sometimes things change. Like about a year ago, we had an interesting fire season. Certainly in the last year, we don't need to be surprised about surprises. And one of the surprises we had last year was waking up to orange skies. And it turned out it was just a certain kind of cloud cover that the smoke gave us for a few days in the Bay Area. It cleared up, and nobody was harmed, at least in the Bay Area. But it certainly harmed our computer vision systems that weren't trained on this data. If you took a semantic segmentation algorithm that was trained on cityscapes data like this and ran it on an orange scene, you got a result that's something like what you see on the right, which is rather poor, right? You shouldn't be, even if the color palette is completely messed up, you don't want your autonomous driving system to suddenly hallucinate random structures in the middle of the frame. So the model that I'll present now for fully test time adaptation was able to do a much better job at recovering from this than other baseline domain adaptation models. And it can still get the general sense that there's a person and a vehicle and some vegetation and so on and so forth in the sky. Here's another example of taking a model that was trained on one data set and then testing it on this orange world environment, and the kind of poor result that you would get in practice, and how the model that I'm about to present improves the results. It's still far from perfect, but it's much, much better. And then one more example. I guess two examples. Okay, so domain adaptation is an important area of machine learning. The problem statement is you're training on one data set or multiple data sets, but then when you're faced with performing at test time, you're given samples from potentially a different distribution, and you still need to do a good job. And there's a number of adaptation schemes that are quite common and important. I mean, obviously, actually, if you do have labels in the test domain, fine-tuning makes sense. There's a paradigm that's been called unsupervised domain adaptation that we've ourselves published in for a while. And then there's what we're now describing now that we call test time training by self-supervision. Let me describe these each in a little bit of detail. So fine-tuning actually is a form of domain adaptation. It's actually great, but it actually requires labels in your target domain, right? That's what it means. That's what this means. So this is out of scope if you're not willing to assume that somebody's going to be annotating your test data for you during the critical time where you need your system to perform. The second class of approaches that we've worked on for at least since 2010, we call unsupervised domain adaptation, where you say there are no labels in the target domain, but still let's do something. And a lot of most of the methods of this class have adopt a kind of alignment approach, where you look at the distribution of the source, you look at the distribution of the data in the source domain, and you look at the distribution of the data in the target domain, and you say, I should probably find a transformation that aligns these two things. And once I do that, then I will overcome I'll be able to align the labels more appropriately and get better performance. So many techniques have used distribution alignment, and most recently adversarial loss-based distribution alignment, learning a GAN-style model where you learn a transformation so that you can't actually predict the domain label that you have in your data. And that works well, but it still actually requires the labeled source data. Actually just requires the source data, because you need to keep around the distribution of the source and and align it with the distribution of the target. And in our newest problem statement of fully test time domain adaptation, we are saying actually all you have is a supervised model, the model parameters, and unlabeled target data. You don't want to carry around the source data and have to do a complicated optimization. So that's fully test time adaptation. It's label free, it's source free, and it's proxy free. We don't assume some oracle is going to tell us what augmentations we can use as a proxy, or that we have labels from which we can cross-validate that. This is appropriate to to ensure accessibility, efficiency, and the accuracy of the learned models. And the core idea here is extremely simple. It says it's just the idea of learning to minimize the entropy of model predictions using a feature-wise affine transformation of the data. So normally we have the situation on the left here, which has model parameters that we learn. And then having learned those model parameters, we simply apply that function to our new data. Here, we learn model parameters, but we also allow an additional optimization to happen on the new data, finding the minimal entropy configuration of the parameters with respect to the test data. And we do that throughout training and testing. So we compute the normalization statistics on the target data, and we update the transformation parameters using the gradient of the entropy objective, and we do this for every normalization layer in the model. So just to give you a very, very simple example, if we are learning a model to classify digits in CFAR, and we train a model without corruption, and then we add corruption to the test data, even just Gaussian noise corruption, we can actually observe the extreme sensitivity to even Gaussian noise of such a model, where you get 67% error versus 4% error in a baseline. Just adding this simple principle of minimizing the entropy of the representation before proceeding to your classification step, this method that we call fully test time adaptation, this reduces the error to 20%. And we can see the example here of what the logit scores would be before in orange and after in blue adaptation, with the true class highlighted here in red. So on the left, there's three examples here, left, middle, and right. On the left example, a 3 was actually presented, but it looked a lot like a 6 until this entropy normalization, entropy minimization approach was applied. And then suddenly most of the probability mass shifted to the correct answer, which is a 3. In the second case, the model initially would have, I guess, predicted a 3 if you picked the mode of that orange distribution, but the true answer was a 2. And in the last example, the model was incorrectly predicting a 4 until it shifted to a 5. So it's not just increasing the confidence, it's actually often changing the predicted, the mode of the predicted distribution before and after the adaptation. Here are some examples on other types of corruption. These are accuracies going from 10% accuracy to 50% accuracy when we add our adaptation. Changing the contrast, we go from 20% accuracy to 70% accuracy. Pixelation, frost, and motion blur, you can see. What's really striking here is how sensitive these models were in their unadapted state to these very simple transformations. The accuracy on the original CFAR model was 79%, and just adding motion blur, frost, pixelation, contrast, Gaussian noise dropped it down to the first numbers that you see on the underneath each of these images: 44% accuracy, 34% accuracy, 23. That a tremendous drop in performance. You wouldn't think that Gaussian noise would harm such a model, but a naive deep learning model is quite sensitive. And of course, you can add invariances to all of these if you know ahead of time that your domain truly is invariant to these kinds of noise. And probably having some insensitivity to Gaussian noise is always a good idea. But you can learn this, you can get the robustness to these without adding augmentations that may potentially be harmful by use of our fully test time model. So here's a breakdown for all the different corruptions and results on ImageNet. The error on the original model would be 22% for a ResNet 50 model. And you can see the performance with different kinds of corruptions, starting off potentially being quite high, almost 100% error, and the performance improving dramatically with our entropy minimization approach. And we get 44%, which was on average, which was significantly better than the prior work at the time we published this, and still is quite strong. An important aspect of our model is that it really is architecture invariant. And it's a very simple idea that we propose. So whatever your deep architecture, you can still apply our TENT algorithm, test time entropy minimization. And we have results across a variety of different models in our paper. And I think in the interest of time, I'm going to skip ahead on some of these things, just show the visualization of before and after, that the representation becomes more separated, which is what you'd like in a classification task. That we also show results on adapting to various digits, including compound digits, and similar results as I've already shown. And adding, I think this is duplicative, unfortunately. And then finally, I'll show some results that are similar to what I started on, where we have training on one domain and testing on another. Here we'd be training on a synthetic computer graphics image and testing on the real world. And you can see there's a significant difference between simulated and real images, leading to performance in the lower left-hand corner, which would be unadapted and quite poor. And our simple entropy minimization technique gives you the result on the lower right-hand corner. I think we may have a video here if I can get it to play. Maybe it's just clicking. Oh, this is showing the stages of the adaptation. Let me go through that again. So here's the first image before the first iteration of the entropy minimization. And as the entropy minimization process proceeds, we can see it slowly becomes closer to the correct result. Okay, so this is wrapping up. Fully test time adaptation is label free. Certainly don't require human annotation. It's source free. It doesn't require carrying around the source model. It's proxy free. It doesn't require knowledge ahead of time of what self-supervised tasks happen to be best in your domain. And it's task and architecture agnostic. And so it can apply to a wide range of models and architectures. And we have a bunch of different ongoing projects, including one that we recently submitted to a conference on using this class of models for adversarial defenses. So if you're interested in that, I'd refer you to Dishwan's webpage, where the archive for that is, I think, recently posted. Okay, so those are the three themes of fully test time adaptation. And I suspected I might have a little bit of time left over. And the other part of my talk I wanted to go through is covering some of our ideas on explainable AI. Not only do we want techniques for unsupervised and adaptive, robust machine learning, but we'd also like to have models that are explainable and trustworthy in some sense. And this is a fun topic because there's a wide range of things that we can mean when we use these words. So hopefully in the next 5 or 10 minutes, I'll at least explain to you what I have in mind when I use these terms. And we can all criticize deep learning as black boxes that don't expose their decision-making process, don't provide confidence in their predictions, and it's not clear how humans, whether they should trust them or how they would correct them. And there's been a usual story when one refers to XAI that says in machine learning, we should have a trade-off, or we have a trade-off between accuracy and explainability, and that you can have high capacity models that are performant but unexplainable, or lower capacity models that are maybe interpretable and explainable, but must by definition be lower performing. And I think that's the wrong way to frame the problem. I'm not actually saying it's incorrect the way it's often framed. If you frame something as an IID supervised learning problem, indeed there's an inevitable trade-off between capacity and performance. And if you equate capacity with interpretability, you could always say, well, a deeper model, a higher capacity model will be more performant. But in the real world, we're mostly concerned about how our models perform in surprising conditions. And most importantly, adding explanations isn't a one-way street, at least not in the view that I have for what is important about explainability. Adding explainability often adds additional supervision to a model, as I'll explain in a few slides. If I force a model not only to solve a task, but to also show its work while it's solving a task. And indeed, I have teachers who are willing to score the model on the work that it's shown and make sure that it's not just right, but it's also right for the right reasons. Well, now I have additional training data, and sort of all the theoretical statements about capacity and interpretability are out the window because I have more training data. And whenever you have more training data, you can do better. So that's my perspective on XAI and explainability at a high level. I like explainability because I think it allows people, users, to actually provide more training signal to deep models. So one traditional and useful part of XAI are saliency models that show what part of an image is significant or even causal for making a prediction. And these can be useful to interpret a model and see when a model makes a decision, like whether it looks at this image and says sheep, or it looks at this image and says cow. You can say, oh, well, when it said cow, it was looking at the right-hand object or animal, and when it was looking at sheep, it was looking at the left hand. That kind of makes some sense. And this is useful in an AI system because you might have a system that makes an error. It may actually mislabel somebody's gender in particular, or make an inappropriate label an image inappropriately, and it might be doing so for the wrong reasons. In this case, if we were to predict the apparent gender of a person, we don't want to do so based on what job they have or what objects are in the environment around them, I would argue. So once you have an explanation interface that shows you what the model is relying on, it allows you to go in and correct the model and say, no, those are the wrong reasons. Here are the reasons of the image. Not only is here's the label, but here's what you should have relied on to make this prediction. So there are two broad themes that we worked on at Berkeley. And here I'm sharing work that was both in my lab, in the lab of John Canny, also the lab of Ankur Dragan. We explored two large families of explainable AI techniques. One that we called introspective or causal models, and those really were ones that imposed structural modularity onto deep learning, and said, for example, might have had an attention bottleneck and said the model's only paying attention to these pixels, and therefore those are what matters in making a decision. And then another class of techniques that we called rationalization or storytelling models that would make a prediction but also generate some natural language around the prediction. And that natural language would be a story, much like a human might tell you a story of why they do something. Why did you decide to take this route to work today, or why did you decide to wear that jacket instead of why did you wear a raincoat and not a raincoat? When asked that question, humans are all going to use natural language to communicate with each other, and so we can just set up that as a challenge. Could a computer algorithm also provide a natural language justification? For example, if you're classifying a bird species, a human would give you a sentence that might describe attributes of the class that are present in the image. And so we can ask a machine vision system to also do the same thing. Or in a driving scenario, when a student driver is learning or being instructed by a teacher, the decision to make a turn or to stop might be explained by the instructor with reference to a driving manual or the rules of the road. And those are the two examples that we worked on at Berkeley. So I think I'm going to only have time to really talk to you about the second one here. So you have a classification model. What type of bird is this? And you could say it's a cardinal because it is a red bird with a red beak and a black face. And indeed, you would want to ground, you can ground the explanation and say, here's where the red bird is, here's where the red beak is, and here's where the black face is. And if you train a model with this, it gives it more training data, and therefore it can have more performance. So we've worked on this for several years and have a line of papers here that have been led by Lisa Hendricks, who's now at DeepMind. And if you're interested, I definitely refer you to all the papers that are shown below. And I'd like to make sure I give you the high-level idea here about what we mean by a visual explanation of this sort of justification type. And it's actually almost an image caption, except it's an image caption which is relevant to a task. But it's not just the definition of the class. It's a description of things that are relevant to the class that are also present in the image. So visual explanation has to be relevant both to the class and to an image. And we can further engage in sort of counterfactuals with this kind of system. We can ask why is it, what kind of bird it is, and get the answer it's a cardinal for this explanation. But we can also say, why isn't it a different type of bird? And get the response, oh, it's not a scarlet tanager because it doesn't have black wings. And the counterfactual pipeline proceeds by predicting the evidence for the counterfactual class. This is a red bird with black wings. This is a red bird that has a pointy beak with black eyes. And then see if you can ground that and figure out what's missing. And that tells you a story that you can then explain as an explanation, a counterfactual explanation of why this is not actually the negative class. So I hope that gives you a flavor of the kind of XAI models we've been building. I'm going to show you just a few examples of some slides for what we've done in collaboration with John Canny's work on extending these ideas from bird classification to autonomous driving. First, John and his student Jin-Kyu Kim had an early work on saliency models for autonomous driving, which could confirm what a driving model was attending to in the image as it was performing steering commands in a causal way. And then that was later extended in collaboration with Anya Rohrbach and myself to build a model that would actually generate textual explanations of why the vehicle was making particular choices. So the output of this model would both be a set of saliency maps and a set of strings, and it would be trained in a supervised fashion in this case against annotated data where humans would explain what driving instructors would have said were the rationales for various driving maneuvers. So let me see if I can get this to play here. And we have the data set that we released on this called the BDDX driving set. And it said the car, first it describes what's happening. The car is moving fast down the street. And then it gives a textual explanation of why is it doing that. So that's an example. I think it's about to turn soon. Now it slows and turns right. And it mentions that there's a pedestrian, and then it stops because there's a traffic in front. Now this is starting to accelerate, so it says the traffic's moving faster. So we can debate what's causal or what's not causal here, but it's certainly interesting to have an autonomous system that has this capability. And I think that's it. And for that video. And importantly, and this is where I think the real cutting edge is right now, as I'm I think reaching the end of my talk, advisable systems are exciting, but they're not as exciting as inverting advisable systems. Excuse me, inverting explainable systems in my mind. Because when you invert an explainable system, you get an advisable system. Because what we just did was create an autonomous agent here for driving control prediction. And we created a mechanism that allowed it to transduce its internal state to natural language. I mean, sort of approximately and fully supervised, but nonetheless. And now we can turn it around in our most recent work, again, in collaboration or led by John's lab. He's built a class of advisable AI systems where humans can give natural language advice to the system, telling it what to pay attention to in words or what specific rules to follow. And that can be incorporated into the system. And I don't have the video for this in this deck, unfortunately, but you can look back at our CVPR paper from last year and the most recent results on GenQ's website and see our results, which essentially allow the human user to give different kinds of textual advice to the model. The one shown here is the earliest result that we had, which is to essentially give textual specifications of what the model should attend to in the moment. And this was important because in the example shown here, the default model actually didn't pay attention to people. The training data that it had, which seems like pretty stupid for an autonomous vehicle, not to know that it should stop when a person is walking in front of it. It turned out in the training data, all the people walked in crosswalks. And so the deep learning model just learned to find the crosswalks and stop. But it didn't realize that there could be people outside of crosswalks, or that even in the crosswalk, you should pay more attention to the people. And so this was something that the explainable interface revealed, and the advisable interface allowed correction through natural language without necessarily having to go collect more training data or construct synthetic data or so on and so forth. So this, to me, is pushing much more towards human-level AI and the way humans train each other and engage with each other. And in the latest work, if you're interested in this, you can follow up by looking at the papers that I referred to earlier. The latest models move beyond instantaneous advice to kind of rule-based advice, where you can specify rules that the system should follow in general, not just in the current instance, and have sort of this high-level advice as well. So that's I've reached the end of the show here, the last slide, and like to just conclude with how do I go? I can't do that. Sorry, how do I do? There we go. And I'd like to thank everyone for listening, and I'd be happy to take questions or have a discussion that might be relevant. I don't see anything on my private chat yet. So looking forward to engaging with everyone.
So first of all, Trevor, thank you. Wonderful talk. A lot for us to digest. Of course, you pointed us the papers, and there's much more there. We probably can get from your webpage those references. There are a bunch of questions. I'm not sure you have time for all of them. But I'd like to start with a question that I'm asking everyone in this, everyone has been in this seminar, which is a very high-level generic question, which is related to how do you think the pandemic has affected research in AI and maybe your research? Is it, I mean, do you see anything special that happened? And I'll give you an example. For instance, we had Maya Matarik here in our last seminar. She said, "Oh, I couldn't work with children." and that was very hard for her to do social interaction. But I wonder, I mean, you do very theoretical research often, but how did
I
affect
think
you?
I think it's been, in many ways, our field was well prepared for virtual work. Many of us work virtually and already had many international collaborations and were used to Zoom. So I think some aspects didn't suffer too much. What really did suffer, I think, were new ideas and integrating new team members into a team. So I think for the first 9 months of the pandemic, aside from sort of just slight depression of losing social stimulation, I didn't see too much negative impact in the group. But then in the last I don't know, 6 months, including through today, because we haven't fully reopened. I mean, we're just on the verge of reopening in California, but our workplaces are still I think the university won't be reopening until September or mid-August. So we have maybe another 2 months to go. So that'll be 8 months. The second half of the pandemic, I feel like projects that were already going continued, but like new ideas I find very hard to create in this environment. I'm just too distracted in a Zoom meeting. So we'll see. So I think we've probably missed out on some big ideas that some collaborative teams haven't created. And there's certainly just more and more emphasis on what's on social media, and I'm less excited about that myself. So that would be my answer, that I think in AI research, things have sort of been a little bit on hold with really creative new ideas, but that the work that had already been underway wasn't hindered that much.
Okay. Also, the next question is sort of maybe a way to bring what you have shown us a little more to the real world. And the question is, I mean, you're talking a lot about unsupervised learning and then you mentioned adaptation. So which domains and applications that we use today are mostly in need of that?
Well, I mean, I think we always think of robotics and autonomous driving, but I could probably tell the story for any domain that you care about. So you tell me what you care about, and is it healthcare? Is it geospatial imaging? Certainly robotics. I'm not sure I have a real story for social media. Like if you have a domain where you have a tremendous amount of supervision, then maybe I have less to say. But the more you have a domain which has where data are really expensive or rare because of medical that's the case, and in some geospatial imaging domains that's the case, or just the robot goes into the room and all the children's toys are in a completely different configuration. Building that general robustness to different configurations and the ability to not be surprised by changing conditions. I think those are the goals that most of us are still pushing on. I mean, anyone who's in the field is aware that while there's so much hype and success that I wouldn't try and deny, things do work well in many cases now, but they also more often than not don't work in many other cases. And that's why it's still exciting to be a researcher. I just hope people don't believe all the public claims that AI is working or that we have AGI around the corner or something like that.
Okay, so I have a question from Gustavo De Mari. In fact, many questions from him. First is, what are the advantages and disadvantages of self-supervised versus semi-supervised learning approach? I mean, what are the two sides of this?
Well, I mean, I guess it'd be great to have a longer conversation and we could agree on some technical definitions of semi-supervised and self. I mean, semi-supervised is a really good approach. I would take semi-supervised to be some combination of clustering. I mean, I think you need both for any real system. I guess you could have semi-supervised without self-supervised. I certainly feel like semi-supervised, like unsupervised alone is almost a meaningless term. So you can replace, when I say unsupervised, you could say semi-supervised. Because to actually do something, you need some supervision or some interaction with the system, in my opinion. And self-supervised is this term for when you can construct a task from the data itself. And it may have this flavor of implicitly expressing an invariance. So I wouldn't put those two terms in opposition. I would say we should always have the best. If you should use the principles of unsupervised learning, which start from clustering or dimensionality reduction, and use them. And then we should add self-supervised tasks, which if you do know they're appropriate for a downstream setting, always do that. Use our Luke method to reduce the risk that you will add a transformation that is not appropriate. And then if you have some labels, the best model is going to be one that is semi-supervised and learns a lot by observing the world. And then as soon as your teacher gives you two or three examples of what a blicket is, suddenly you know what a blicket is. And so that's how language grounding works, apparently in humans. And that's what we need in an AI system.
Good. So we have a question from Fernando Osorio, who was helping with us backstage back in the beginning. Saying data augmentation, adversarial learning are traditional ways to expanding in an initial supervised data set, providing, and then he quotes, unsupervised example. How that compares, how that fits in the self-supervised and unsupervised models that you described?
I mean, I think adversarial learning is a form of unsupervised learning, generative modeling, and I think that's complementary work that we would, still to be added to our approach. Data augmentation, I think, is very, very much the same idea that we were discussing in self-supervision and contrastive learning.
So, more generic question from Gustavo Demari. He says, in your career, you've partnered with many universities, many companies. So could you give some tips to this, mostly Brazilian researchers in this crowd, to what to do and how to do research in this kind of partnership, and especially with international partnerships? Well, I mean, I think that's a real case.
That's the real. If there's going to be an upside from the horrible pandemic that the world has experienced, it will have further lowered the barrier to collaboration, and because we've proven how effective virtual work can be. So the best international partnerships are to find a collaboration where something is a meaningful exchange. The downside of COVID, the current world, is that many of those interactions happened in person at conferences. So hopefully we'll have the best of both worlds when we have the full reopening and young researchers can meet other researchers again, come up with ideas in a conference floor, and then go back and work remotely. I don't think there's as much of a need to physically travel. I mean, eventually you should travel to work together, but at least half of it or a significant fraction of the work can now be done virtually. So the tips would be find a good research collaborator. Hopefully your advisors might have some connections, and propose a virtual visit to a lab for a period of time and start writing papers together. And then actually visit in person.
Yeah, in fact, one thing that I thought was good that happened. It lowered the barrier to have talks from international professors, people like you,
Correct.
in a way that compared to before, I mean, we probably would have to fly you here to Brazil, and
yeah, it was considered inappropriate to just call it in.
Yeah.
And now it's considered appropriate. And in the future, I think it'll be half-half. Like
Yeah.
half the time I do want to travel, and half the time I would rather not.
No, and also, I mean, the fact now also, I think that we are recording. I think we are creating a very interesting documentation about how ideas are progressing beyond papers. You know, in the sense, from the way people talk, from the opinions people express. And I think that's a very positive thing. If you don't mind, we have some more questions.
Sure.
I have a question here about your work on in terms of augmentation. Is how much knowledge is already in the choice of the augmentations you allow to have?
That's exactly the right observation and the point of the first. Yeah. So right. I mean, there is some knowledge in those augmentations, and at least with the Luke method, we're saying you don't need to know which ones are relevant. But it's true. There's some. We haven't explored kind of completely random generation of augmentations. That would be useful to consider.
It's more like here's a toolbox, right? Kind of approach. There's a toolbox.
But the tools are hand specified.
Yeah.
So,
and find the right
tool. We could probably generate random tools and just do complete brute force search in some space.
Yeah. I also think some of the work that Josh Tenenbaum is doing of random programs is also interesting for this. But let me continue here. Still a lot of questions about the first part of your talk. This is also this from Paul Kuster. I hope I haven't botched your name. Could you comment about detecting or recognizing motion objects using the kind of approach? I mean, the first step of the adaptation. Could you use the previous frames for learning changes in environment? This very short-term adaptation, I think, that's what he's talking about.
Learning changes in the environment. I guess I'm not sure what kind of changes we're talking about. But of course, we can use motion for change detection. Claudio and I and others at MIT were working on that many years ago.
No, I think he's applying the recognition stuff for video. Let's put it this way: you're talking about recognizing birds and dealing with change in the environment of static pictures. So, what about videos?
Yeah, I think it's a very important problem, and I certainly would say yes, you can use the previous frames for learning changes in the environment, but I'm not sure how it relates to the talk I gave today. We have an interesting project we published a few years ago on trying to do natural language for captioning a change in the environment, where that's sort of related to the bird description system, where you put two images in and a string that explains the difference. And so you basically try and learn a captioning system that can do change captioning. So the paper title there was called Robust Change Captioning by Seth Park and colleagues.
So Gustavo has also another question, which I'm going to reframe slightly, but do you think that the self-supervised learning can help to tackle some of the challenges on sample complexity in reinforcement learning?
I mean, a lot of people believe that, and Peter Abeel has a couple papers. So generally, yes, and that's where the biggest need is, because reinforcement learning is so sample inefficient in its traditional forms. So, yep. But my lab doesn't have a specific result on that. But I know that Peter Abeel's lab has explored that, and they had some some early results that showed MoCo and SimClear types of models could directly be integrated into reinforcement learning.
I've been working on reinforcement learning recently.
I have a few students, but nothing that I'm going to talk about now.
Okay. No, because
we
it's
had a couple
area.
Great papers on exploration, the Deepak Pathak led. You could debate whether that's reinforcement learning, because the whole point of the paper was that you had no reinforcement.
Okay, good. This was where? Papers, archive.
I think it was ICML was the first.
Okay.
ICML 19.
Okay, good. I think I'm going to get one last question here from Angela Mendes. He's asking, when the models adapt the new samples using your fully test time strategy, does it have a way to not overfit on the new data and forget what's learned previous? I mean,
oh, that's a good question. Also, the one you selected was I like both questions. We should be doing that, and we have a research project on predicting generalization that we just submitted to ICCD, but these are currently separate, and so our future work is to try and combine them. And so that's the question that's written on the screen right now. And I think you asked me a question about forgetting and continual learning, and whether we can avoid that. And the adaptation work is silent on that, but I think the explanation ideas, one thing we've explored is doing continual learning, which we call remembering for the right reasons. And we have a paper at iClear just now on that, where we do a experience replay model, which replays not just the supervision, but also the rationale or the explanation, and requires that the explanation be consistent. That's actually in some sense, one of the most recent and coolest XAI work that I have that I didn't actually get to include in this talk.
Okay, so I think we already used a lot of your time. I just want to make a comment that when I saw your explainable AI driving, I couldn't stop to remember of driving with my brother, that he would say all the time, "Look at that guy! Look at it! Someone is crossing! Someone." It feels like the paradise for those people to be able to do that for
backseat driver. I think we heard that phrase.
Exactly. Yeah, that's so now you have you can be a backseat driver and have a very patient driver who can handle that. But anyway, I think that's really an interesting model of cooperating, of engaging in different modalities with an autonomous system. And yeah, I would love to see that in the real world, working in a real car at some point. So I'd like to ask for a virtual round of applause to Trevor. And thank you for your time. Thank you for being part of this seminar. Just to finish, this is the Perspectives in AI seminar of the Center for Artificial Intelligence of the joint project of University of São Paulo, IBM, and FAPESP. This talk will be made available in a few days in our YouTube channel. And please sign in for our LinkedIn accounts or Facebook accounts to know about the next talks, the next Perspectives in AI talks. We have one special for the Brazilian crowd next week. We'll have all the directors of the recently announced AI centers in Brazil. They are going to be together talking with us about policy of AI in Brazil, about academic perspectives. This will be in Portuguese, talking in Portuguese. This will be next week, the 24th, at 5 p.m. Brazilian time. Again, thank you, Trevor.
Thank you for having me.
Hopefully we will have a coffee someplace in some conference soon. Thank you.
Looking forward to it. Bye-bye.
Bye-bye.